but this is not hard, so I assume that everyone's getting it. A path is nothing but a sequence of vertices such that there is an edge between every pair of vertices. So for example, here BAD is a path. BABCD is also a path. Right? So a path is just a sequence of vertices such that there is an edge between every pair of consecutive vertices. A graph is said to be connected if there is a path between any two vertices in the graph. Okay, so for example, this graph, this Königsberg graph or multigraph is connected because we can start from any vertex and we can reach any other vertex. But suppose there were two other vertices, or say let's say three other vertices like this, and if this whole thing was our graph, then this graph would have been disconnected because there is no way for us to start from this vertex over here and reach any of these four vertices. But when a graph is not connected, when a graph is not connected, it's going to have multiple connected components. So this is one connected component. So connected component is basically a subset of the vertices of a graph such that there is a path between any two vertices within that connected component. So there are two connected components in this sort of bigger graph. Okay. Another term is cycle. A cycle, as you can expect, is just a path which ends at the same vertex from where it starts. Right? So BADCB is a cycle. BAB is also a cycle. Now here's a question for you. Could you ever have a graph in which there is exactly one vertex with an odd degree? Remember that the sum of the degrees of all the vertices is twice the number of edges. The degree of a vertex is the number of other vertices that are connected to this vertex through an edge. So can you ever have a graph in which you have exactly one vertex with an odd degree? Yeah. 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 The sum of the degrees of all vertices should be an even number, and if there is only one of these numbers that's odd, then when we add then the sum of all the other numbers is going to be even because they're all even. So when we add an odd number to an even number, we get an odd number. So the left hand side is going to be an odd number, but the right hand side is going to is as we know an even number, and that's not possible. So we can't have a graph in which there is exactly one vertex with an odd degree. Okay, so the answer to this is no. Here's a slight extension to the problem, to the same question. Can you ever have a graph in which there is an odd number of vertices with an odd degree? So instead of one, you have an odd number of vertices in general with an odd degree. So can you come up with like edges here to illustrate such a graph? So let's call this as vertex 1, vertex 2, vertex 3. How will you add the edges here such that all three of them have an odd degree? Oh, okay. So do you see the reasoning? It's very similar to the reasoning here. Yeah, because if you have an odd number of vertices with an odd degree, then the sum of the degrees of those odd number of vertices is going to be an odd number, right? So if you sum an odd number of odd numbers, you're going to get an odd number. If you sum an even number of odd numbers, then you get an even number. But if we have an odd number of vertices with an odd degree, the sum of the I'm starting to get an echo, Biswaji. Hello? Yeah, now it's okay. Now it's fine. So if there's an odd number of vertices with an odd degree, then the left hand side will again be an odd number, because the sum of the degrees of these vertices is going to be an odd number, and the sum of the degrees of the other vertices is going to be an even number, and an even number plus an odd number is an odd number. So the left hand side is an odd number, but we know that it should have been an even number by this equality we just proved some time back. So this is also not possible. So because of these two sort of assertions that need to be satisfied in any graph, we can say that the number of vertices with an odd degree must be even. In other words, it can be 0, because 0 is an even number. It can be 2, it can be 4, it can be 6, and so on. So let's return to the Königsberg problem. Now here's how Euler reasoned that there does not exist such a path in the Königsberg graph which crosses every bridge exactly once. Here's a claim. Okay, assume that there is such a path in the graph, okay, which crosses every bridge exactly once. Any vertex, in that case, any vertex with an odd degree in that graph must either be the starting point or the ending point of the path. Why is this true? Yeah, sure. In that case, we'll say that the degree of that vertex is even, because it's so that self loop will contribute 2 to the degree of that vertex. But right now you can just assume that there are no self loops for simplicity. Actually, even if you assume there are self loops, I mean, nothing's going to change. I mean, the answer is going to be it will remain the same. So what we are saying here is that if there is such a path in the graph which traverses every edge exactly once, then any odd degree vertex in that graph must either appear at the very beginning of the path as the first vertex, or the last vertex, or the ending point of the path. In other words, a vertex with an odd degree cannot appear in the middle of the path. Okay, so if we say that the path had, say, k vertices, let's say this vertex is v start, this vertex is v end, and if we have a vertex with an odd degree, now it is possible for it to appear in the middle, but it must appear either as the start vertex or as the ending vertex, because you may return back to that vertex somewhere in the middle, but then you will also get out of that vertex. but it's not possible for a vertex which is neither the start vertex nor the ending vertex to appear in the middle. It's not possible for a vertex with an odd degree to appear only in the middle. You can't have an instance where an odd degree vertex appears in the middle, but it does not appear at the either as the starting vertex or as the ending vertex. Anybody